Right, my name's Mike Charlton. I'm a professor of experimental physics here at Swansea. I'm also a research fellow of one of the research councils in the UK, and currently I'm also head of the physics department within the College of Science. Within that department, I'm also head of the experimental physics group, and in particular a group of four or five of us who've been involved in anti-hydrogen research at CERN. We have a lab here at Swansea where we develop some of the techniques that we use elsewhere. A lot of our research is based out at the European Particle Physics Laboratory. It's called CERN in Geneva. So we develop stuff here and take it out there, and vice versa. So there's a crossover between the two areas. Basically, we're looking for a chink in the armor of the laws of nature. And so in some cases you do that by accelerating particles to tremendously high energies, like at the Large Hadron Collider, and trying to recreate the conditions of the early universe. But the other way to do it, and the way we do it, is to study objects which are reasonably familiar to us, but in incredible detail, looking for differences between one thing and another. Sometimes it's theory and experiment, sometimes it's two atoms which are supposed to be the same. The way CERN works is that it provides you with beams of particles and an infrastructure in which you can work. But you have to do the rest. You have to build your experiment around what they provide. And so we tend to build instruments and apparatus in our own laboratories in the UK, and our international collaborators will do the same for different parts of the experiment. We make sure they work, we transport them to Geneva, and then we reconstruct the bits that we have built with the bits that our collaborators from other countries, the USA, Denmark, Japan, all over the place, we put them together to make a much larger piece of apparatus that we couldn't possibly have had the know-how or the funding to construct alone here in the UK. What we're trying to do is make very precise measurements on an atom, but this is a very special atom. This is an atom that we've had to construct ourselves entirely out of antiparticles. And we want to measure the properties of that anti-atom for a particular reason. And it's taken us 10 to 15 years to be able to put those antiparticles together in a way in which we can control what happens to the anti-atom after we've made it. So just recently we've had a major breakthrough with this, and we've been able to effectively hold this atom, which, should it ever hit any matter, will annihilate immediately on impact. We've been able to hold it in a kind of a bottle and store them for several minutes at a time and perform the first ever experiments on these things. So my work is kind of an evolution. The germ of an idea 25 years ago is evolved into a project involving 40 to 50 people. The area of physics that I'm working in, this small area, there are now several hundred people working this from all around the world. All of the experiments at CERN are multi-university and sometimes other national lab collaborations, because they're really quite large. But each university and each team brings its own expertise, and we have a particular expertise here with the antiparticle of the electron called the positron. That's what we're best known for. However, that was just like a ticket to get onto the bus. We now developed expertise as a result of being involved in this enterprise in other areas. So we bring the expertise that we had and we've developed to bear on the scientific challenges that are ahead of us. But it's a very, very familiar thing in physics to pool talent to achieve something that you couldn't possibly do on your own or even within your university group, because Swansea is famous for certain aspects of physics, but in order to achieve what we want to achieve, we need to have scientists working alongside us with a common interest in the final goal, but with other areas of expertise which complement ours.